Okay, so for a lossy line, propagation constant as a function of position is equal to propagation constant at the load into e power plus 2 gamma z. And we can also represent it in this manner. So we know that this gamma over here is complex number having a real part alpha and imaginary part beta. So propagation constant as a function of z is equal to e power 2 alpha z e power plus j 2 beta z. And sometime, because this z is actually related to the position, but that position can also be related to the length of transmission line. And we can replace z by minus L because of the reason, if I draw that transmission line again, because we represent our axis like this. So at this point, z is equal to 0, and at this point, z is equal to minus L. But we know that length of transmission line can never be negative. So actually, when you are at this point, so at this point, we know that L is equal to 0. It means the length is 0. And when you move towards this direction, so now it means that the length is increasing. Length is increasing. Okay. So Z can be replaced by minus L. So if I represent this propagation constant as a function of L, so then you can write this as e power minus 2 alpha L e power minus j 2 beta L. So now we have represented the propagation constant in terms of the length of the transmission line. This expression is telling us that on a lossy transmission line, the amplitude, this is the amplitude part, okay? You can see that propagation constant is a complex number, and this term is going to be is going to decide the amplitude or magnitude of the propagation constant, and this term is going to decide the phase of the propagation constant. And because you already know from signal and system course that this function, this represent a decaying function. So it means the magnitude of the reflection coefficient, will change as you move on the transmission line. And if you remember, when we were talking about lossless transmission line, so on a lossless transmission line, the magnitude of the reflection coefficient doesn't change. It remains constant. Whether you measure reflection coefficient at the load point or at the middle or at the input, the magnitude part of the reflection coefficient was constant. But now, for a lossy line, the magnitude will not remain constant. The magnitude will keep on changing. At each and every point, the magnitude of the reflection coefficient will be different. And of course, phase is changing. Even for a lossless line, we found that the phase of the reflection coefficient was not constant, it was changing. And in case of lossy line, we get the same behavior, that phase will change depending upon the value of L. Okay. Now, using the same figure, I'm interested now to find out how much is going to be the impedance at this point. Okay, so if I stand over here and find out and look towards the load, so how much will be Zn? because I want to find out impedance at the input. So I can take the ratio of voltage at this point and divide it by the current at this point, and that ratio will give me Zn. So how I will find out Zn? I need to find out how much is the voltage at Z is equal to minus L, and then divide it how much is the current at this position, which means I have to take Z is equal to minus L, which is this point. Now I have already written the expression of voltage and current in a general manner in the previous session. So just substitute, just replace Z by minus L. So you will get V naught plus e power plus, so e power plus gamma L plus reflection coefficient e power minus gamma L. This is the voltage, and then you write down the expression for the current at Z equal to minus L. So you get E plus gamma L minus reflection coefficient e power minus gamma L. So wherever you are seeing this L, what I have done is I have replaced Z by minus L. Okay. So in the general form of voltage, you have minus gamma Z. So minus gamma Z become plus gamma L. Okay. Now you can simplify this expression. This will cancel out. So Z in, this Z naught can be shifted to the numerator. And then what you can do is you can take E plus gamma L as common in the numerator, and similarly you can also take E plus gamma L as common in the denominator, and these common terms will cancel out, and what will be left, so you get 1 plus gamma, because you have taken this as common, so this will become e power minus 2 gamma L. Okay, and in the denominator you get 1 minus gamma e power minus 2 gamma into y. This is one expression of input impedance for a lossy line that you can use. Okay, but there is an alternate form, and that alternate form can be derived by replacing this gamma. So we already know that the gamma that I'm using over here, it is the reflection coefficient at this point, that is at the load point. And we know that reflection coefficient at load point is simply equal to ZL minus Z naught ZL plus Z. So what you can do in this representation, you can replace this gamma and this gamma by this result. And then of course you have to take LCM ZL plus Z naught. You can take as LCM, and then you can simplify it. And this function, exponential function, can always be represented in terms of sine and cosine can then be represented in terms of tangent function. So what I will suggest is you can represent this in alternate form as, so if you do the substitution that I mentioned, this input impedance expression can be converted into this form. ZL plus Z naught and you will get tangent hyperbolic gamma L, and in the denominator you should get Z naught plus ZL tangent hyperbolic gamma L. This is an alternate form. So one possibility is you can use this one, and other possibility is you can also make use of this expression to find out how much is the input impedance at the input of our terminated lossy line. Now let's make a comparison so that you can get a bigger picture. When we consider an ideal line, so Z naught beta. So this is a lossless line, and when it was terminated with some load, and we do the same analysis, the input impedance for this was, so there were two expressions as well. So we derive these expressions. Z naught 1 plus gamma e power minus j 2 beta z divided by 1 minus gamma e power minus j 2 beta z. And we also derive this alternate form, Z naught ZL plus j Z naught tangent beta L divided by Z naught plus j ZL tangent beta L. This was for a lossless transmission line. So this first one, this is for a lossless line. And if you go back, this expression is for a lossy line, and you can now compare them together. So they are almost similar. Zn is Z naught 1 plus gamma e power minus 2 gamma L. Whereas in this case, we get 1 plus gamma e power minus j 2 beta z. Because for this case, we know that alpha is 0. And similarly, if you look at this expression for a lossy line, you have ZL plus JZ naught tangent beta L in the numerator. But for a lossy line, you have ZL plus Z naught tangent hyperbolic gamma L. So you can see that we are having gamma over here, and we are having beta, only beta over here because of this reason. Okay. For lossy line, this alpha is not equal to 0. Because of that, you can see the corresponding changes in the expression of the impedance equation. So this is something which you need to understand, that when you are analyzing a lossless transmission line, which equations you are going to use, and when you are analyzing a lossy transmission line, so which equations you are going to use. And also you need to understand that how we derive these expressions. Okay, you don't need to remember them. You can always derive them, as I have done in this particular lecture. So this is the comparison of lossless terminated line and lossy terminated line. Now, for a lossless transmission line, if I'm interested in finding out how much power is transferred to the load, because this is a lossless line, so if I find out how much power is available at this point, the same power will be available at the load because there are no losses. So if I find the input power, if I find out the expression of input power, this is going to be the same as output power or load power because there are no losses. But in case of lossy line, in case of lossy transmission line, whatever power is available at this point, the same power will not be available at the load point, because when this signal travels through this line, some part of the power will be wasted within the transmission line. So let's find out how we can quantify this power, how much power is going to be available at the input of this lossy line, how much is going to be available to the load, and then from these two powers, that is input power and output power, once we know input power and output power, we can always find out how much power is wasted or lost in the transmission. So let's do that. So power calculations. So first I will find out power delivered to the input of this line. Power delivered to the input of the terminated line. That is at Z is equal to minus L. Because I'm interested in finding out power at this point, so it means Z is equal to minus L. So I can make use of the general expression of power, that is Pn. So let me use this symbol for input power. So Pn is equal to 1 by 2 real part of how much is the voltage at input. So that voltage must be equal to voltage at Z equal to minus L multiplied by how much is the current at that point, that is at Z equal to minus L, and we have to take the conjugate of the current. So this expression, once we simplify it, we will be able to find out how much power is available at the input of when we connect a source or generator. So how much power generator or source will be delivering to this point, we can find out with the help of this expression. Now we already know the expression of voltages and current, so I'm not going to do that. So you already know how to find voltage at Z equal to minus L and how to find current at Z equal to minus L. We already have those expressions. If you go back to my previous discussion in the first session, you will find out that we have expressions for V of Z and I of Z. So all you need to do is substitute Z is equal to minus L and then multiply them together. And in the end, you need to, this multiplication of these two will be some kind of a complex number. So because we are talking about active or real power, so you need to take the real part of this complex number. So I'm just going to write the answer, and I suggest that you do this on your own. This is not a very complicated thing. You will be able to do it. So the final expression that you will get will be V naught plus magnitude square divided by 2Z naught into 1 minus gamma L magnitude square into e raised to power 2 alpha L. So this Pn, after you use V of Z equal to minus L multiplied with I Z equal to minus L and then take the real part, this is what you will get. Now, how much power is going to be delivered to the load? How we are going to find that? So power delivered to the load, that is at Z equal to 0, because in our case, yes, this is our load. So how much power is going to be there between these 2 points? It will be, this position is z equal to 0. So all we need to find out how much is the voltage at this point and how much is the current at this point. So using the same general expression, this one. So for this particular case, you will say power delivered to, let's call it load, it must be equal to 1 by 2 real part of voltage at z equal to 0 multiplied with z current at z equal to 0, and we need to take its conjugate. So this is the same idea. Okay, previously we were using z equal to minus L, and now we are using z equal to 0. So all you need to do is substitute z equal to 0 in the general expression of voltages and current, multiply these two expressions, and then finally take the real part. So this will simplify to V naught magnitude square divided by 2z naught into 1 minus gamma magnitude square. So this is the expression that you can use to find out how much power is going to be delivered to the load on a lossy transmission line. Now, one thing that you need to identify is, in case of input power expression, the reflection coefficient that you are going to use is gamma L. Gamma is a function of L. In case of power delivered to the load, you can see we are simply representing it with gamma. And I have clearly pointed out this before, said gamma is the same thing as gamma of 0. So by default, gamma will always mean gamma which is computed or calculated at z equal to 0. And in our case, z is equal to 0 will always mean load position. Okay. So you should not confuse this thing that this gamma L and this gamma is the same thing. They are not the same thing. This gamma is the gamma at this position, and this gamma L is the reflection coefficient at this position. So if you are standing over here, you are going to get the reflection coefficient gamma L. And if you are at this point, this is going to be gamma. Okay. So once we know the general expression that this is the power which is available at the input, and this is the power which is available to the load. So now we have a very simple situation that we know P in, we know P load. So in case of lossless line, we know that power delivered to the load is the same as power available at the input. But now we are dealing with a lossy line. So in that case, the load power will always be less than input power. Load power will always be less than input power because some of the power is going to be wasted. So if I'm interested in finding out how much power is lost in the transmission line, I can simply find this power by subtracting P in, that is by subtracting power delivered to the load from the input power. So whatever difference is between P in and P load, that must be power which is lost in the transmission line. So P in minus P load will give us power lost. Okay. So now we have P in, we have P load. So all you need to do is this is P in. So take this expression and then minus and then put this expression. And then you can, yeah, always, because this term is going to be common in both expression, this v naught plus magnitude square divided by 2z naught. Similarly, you get this thing. So this term will also be taken as common. And let me write down the result, what you will get from this. After simplification, power lost will be equal to v naught plus magnitude square divided by 2 times characteristic impedance, and you will get this thing, e power 2 alpha l minus 1 plus gamma square 1 minus e power minus 2 alpha l. Now, this is the final result that you will get. So, uh, you people can always simplify this, but let me give you some guidelines how you will arrive at this expression. In case of Pn, so what is the expression of Pn? Pn is this thing v naught plus magnitude square 2z naught and then gamma l. So you can see in this final expression, you don't see gamma l. You don't see gamma l. So where has gamma l gone? We have already proved this thing, that this gamma l is equal to gamma at the load position and e raised to power 2 gamma l. Today I proved this expression. So what you need to do is, in place of gamma l, you can use this thing. So you can see you get gamma. In load case, you already have gamma. So now you can see that this gamma is there in this expression. Okay. Now we can also see another important pattern in this expression. So power loss. So power loss is P in P load. Okay. So you can clearly see that this power is the power that is going in the forward direction. And this is the power which is reflected back. Okay. So on a transmission line, some power is going in this direction and some power is going in this direction after reflection from the load. So on this lossy line, there are two waves or signals which are traveling, one from left to right and another from right to left. Now this signal which is traveling in this direction, it is also going to undergo attenuation or loss. So this, how much loss is uh, taking place for this wave which is traveling in the forward direction. So this part, this one, this expression is representing the power wasted or power lost for the forward wave. Okay. And this expression, this part of the expression is telling us how much power is going to be wasted when the signal is traveling in the backward direction or in the direction towards the generator. Okay. So these two terms, you can always assign a physical meaning to this expression. So this, why we have two terms in power loss, why we have two terms in the expression of power loss in a lossy line, because when you connect a mismatch load, so on that transmission line which is terminated by a mismatch load, power will be traveling in the forward direction as well as in the backward direction. Now, whether power is traveling in the forward direction or whether it is traveling in the backward direction, because it is traveling on a lossy line, so it will undergo losses. Okay, so these are forward losses and you can call them as backward losses. So total loss will always be forward loss plus backward loss. Any questions so far?
No, sir.
Okay. Let me move on to the next chapter, which is the chapter 5 of the textbook. And the title of that chapter is Impedance Matching and Tuning. So we have already talked about this concept of microwave engineering, that whenever you design a microwave circuit, so you will come across a problem, and that problem is known as impedance mismatching problem. And as a microwave engineer, we will never design a circuit which is having this problem of impedance mismatching, because impedance mismatching represent a wastage of power. You don't want that power from the source or transmitter is wasted. Your goal is to ensure that whatever power is generated by the source, it should reach to its destination, and that destination is of course load. So in order to find a solution, so it will not be possible always that you design a circuit and it is completely matched to the load. So in a general situation, your circuit will not be matched to the load. So in that case, you have to design a circuit that will solve the problem. So you will design an impedance matching circuit that will ensure that your system or your circuit is matched to the load. And in this chapter, we are going to talk about what are possible impedance matching circuits. And we will find that there are a number of options available to you as a microwave engineer. So there are maybe circuit number one, circuit number two, circuit number three. So you have options, you have multiple options to design an impedance matching circuit. But as you know, every circuit will have its own advantages and disadvantages. So as a microwave engineer, you should be aware of that if you select a particular impedance matching circuit, it will have some problems, it will have some limitations. So to solve a particular problem, you have to select a proper impedance matching circuit. So not every you cannot use same impedance matching circuit in all situations. Okay. So depending upon the problem and application, you have to find out which particular impedance matching circuit is suitable for this case. Okay. Also, you also need to understand this point that in some cases, no matter what you do, your circuit will not is not going to be matched, even if you use an impedance matching circuit. So we will also talk about what is the necessary requirement that your mismatched load will be matched. Okay, so you cannot always think that if this is an impedance mismatching problem, so I will be able to find its solution. There will be possibility. There is a possibility that you are looking at a problem where the solution doesn't exist. So this is also important. So let me go through this whole concept one by one. So let me draw a figure with respect to which we will understand the importance of impedance matching circuit. So the problem is there is a circuit which I'm representing with this transmission line. This transmission line is having characteristic impedance Z naught, and you want to connect it to a load which is represented by ZL. And the problem is your system or your transmission line, which is represented by Z naught, and your load, which is represented by its impedance, they are not equal. So ZL is not equal to Z naught. So we call this problem as mismatch, or let me call it appropriately as impedance mismatching problem. And what is the effect of this on your circuit? So what is going to happen is any signal which is coming from the source side, you want that signal to be totally transferred to the, or to be totally delivered to the load. But because ZL is not equal to Z naught at this point, there will be reflection coefficient not equal to 0. So now when this signal arrives at this point, some portion will be absorbed by the load. So some power is delivered to the load, but now you also have signal which is traveling in the reverse or backward direction. So we don't want this to happen, because this signal which is traveling back to the source, this is kind of wastage. Our objective is that this signal which is coming back towards the source, it should not be there on the transmission line, because ultimately what is going to happen in a broader sense, so this is now we have a system where the signal is traveling in both directions. So we have forward wave, backward wave, and these two waves are going to combine together, and they are going to create what we call as standing waves. So standing waves are undesirable. Whenever you have this problem, that is, your load is not matched to the system, there will be standing waves, and standing waves is an indication that your circuit is not efficient. It is not a reliable circuit. It is kind of an inefficient circuit, because power is going in the undesirable direction. Okay. So this is the problem that we called as mismatch, impedance mismatching problem. So what is the solution? Solution is overload ZL should be equal to Z naught, but we cannot change the load. Overload is ZL, and our system characteristic impedance is Z naught. So we cannot change ZL or Z naught. So what we want is that even if ZL is not equal to Z naught, we should design a circuit so that there is no standing waves. Okay. So what I will do is to represent it in a block diagram form. So I will say what we will do is, what is the solution to this problem? So